Okay, so electrical potential of a point charge. Okay, so if you look at your notes, you'll notice that we've got this mass, and we've got it at this 10-meter height. So what is this mass going to do? Okay, and specifically it's going to have what kind of motion? Okay, it's going to have acceleration in that direction. It's going to accelerate downward. So the equation for it, we'll put a little, that's supposed to be an arrow symbol, okay, above the F and the G, meaning those are vectors, okay. Whoa, this printed out differently. That's not good. Okay, that's all right. These little symbols here, they're supposed to be arrow symbols. Okay, for some reason they didn't print out the way they were supposed to. Okay, did they print out okay on yours? Okay, good. Those are supposed to be arrow symbols, meaning that those are vectors. Okay? And for some crazy reason, they got cut off and made rows. Okay? All right. So here's what we'll do. We're going to look at the gravitational potential, what it really is in the gravitational world. It is, by definition, the gravitational potential energy divided by the mass. It's that ratio. All right? So if I take mgh and I divide it by m, I get the gravitational potential as literally gh. So the gravitational potential is gh. You don't need to know that for this class. All right? But it's important to know to compare it to the electrical potential. All right? If I divide both sides of the gravitational potential by h, I get g, and g is a gravitational field. All right? So, which is a constant. Yes. Well, it's a constant near Earth. Yeah. And it's not always a constant when we're dealing with electrical potentials. Okay? So, the whole idea behind this left-hand side is to prove this here, that the gravitational potential divided by the height is equal to the gravitational field. That's the whole idea behind the left-hand side. All right, does that make sense? Okay, so with that being said, let's look at how that applies in the electrical potential world. All right, in the electrical potential world, if I got this positive charge near this negative plate, and it starts with initial velocity of 0, what kind of motion would I expect it to have? Acceleration. Okay, acceleration which way? Okay, so it's going to accelerate to the right like that. All right, and remember how we defined V. We defined the potential as being what actual value? Or as being V, but we said that V is equal to what? EPE over Q. Good. It's the electrical potential energy per unit charge. All right, and we'll assume that this is a test charge here. Okay, so we'll put a little sub-zero there. So it's a test charge. So just like in the gravitational world, if we divide V and divide it by D, the distance, just like in the gravitational world where we took the gravitational potential and divided it by H, what do you think that will equal? Okay, in the gravitational world, it equaled the gravitational field. What do you think it's going to equal in the potential, or it's going to equal the electric field. Okay, so this is the electric field. Now, the reason I show you that is that this may come up on the AP test. All right. Now, let's look at how something that needs to be explained. There's a negative sign here, and I need to explain where that negative sign comes from, because it actually comes up on the AP test. All right? So let's go back. Let's look at the next set of notes where I've got this setup here where I got, once again, a positive charge and a negative plate here. Right? So these are the potentials. They go from 10 volts to 5 volts to 0 volts. The distance relative to the object goes from 0 meters to 5 meters to 10 meters. In that setup, what does the electric field, what direction will it point in? Left to right. Okay? It'll point from the left to the right. Does everyone understand that? Why that has to happen? Because it's based off what? Yes, it's based off what a positive charge would do. So this is the direction of the electric field. Okay? So it's going from the left to the right. So notice, what does the potential do? What does the potential do? Let's look at these potentials. What do these potentials do in the direction of the electric field?
Increase as your distance gets bigger.
Well, in the direction of the electric field, though, what's a potential? In the direction of the electric field, the potentials are doing what? They're decreasing. So we want to say that V decreases, so this is important, decreases in the direction of the electric field. Okay. Now, if I look at this example, let's look carefully at what the distance does, though. Relative to where I'm letting go of it, it's actually going some positive distance to the right, whereas the electric potential is decreasing. So if I take my equation that I said before, and I'm going to do a delta V over a delta D, and I set that equal to the final potential minus the initial potential. So the final potential in this setup would be what? What would the final potential be?
0.
Okay, 0V, and the initial potential? Okay, so I'm going to subtract 10V from that. Okay, and then what's the initial, or what's the final position, I should say? 10 meters. And the initial position? Okay, 0 meters. So what kind of answer does that give me? Okay, that gives me an answer that has a negative in it. We need to get rid of this negative sign. All right, so we need to get rid of that. Okay, get rid of negative sign. The whole reason we need to get rid of that negative sign is that we have to make sure that the electric field points in the correct direction. So to get rid of that negative sign, what do we actually put into the electric field, this version of the electrical field equation? How do you get rid of a negative sign? Yeah, we put another negative sign there. So we put a negative sign there to get rid of the negative sign that we would normally get in calculating this. And the whole reason we do this, okay, it's because of that chargism we talked about before in the electric field world. Everything is based on what? Yeah, everything is based, electric field is based on a positive charge. Based on positive charge. So this actually comes up why you have to have that negative sign there. Okay? So this is another equation that we can use that relates the electric field and the electric potential. I won't show you any examples of this. They turn out to be pretty easy problems, but realize that that's another equation that we can use. Okay? All right. Now, let's look at a very specific example. This example has, in all regions in this example, notice that in all regions the electric potential is the same. When the electric potential is the same, what can we say about the electric field? Yeah, it's the same, but it's actually a very specific value. If the potential, put it in the equation. If the potential is constant, then exactly, it would be 0. If the potential is constant, the electric field has to equal 0. Okay? That's really helpful for us in our notes.
How would this potential there if there's no electric field?
It'd have to be generated somehow. right? And we're not concerned about how it's actually generated. It's just generated somehow, right? Completely theoretical. Okay, so let's look at this example now. Okay, so I've got a negative charge on the far left-hand side. I got this place I'm going to call location 1. That's 1 meter away from this negative charge. And then location 2, which is 2 meters away from this negative 1 Coulomb charge. My first question is going to be, what is the potential at location 1 and what is the potential at location 2? Look really carefully at your equation sheets because you'll notice that there's an equation for the electric potential. Okay? The equation for the electric potential is actually this. This is the equation for the electric potential for just one charge. It's just KQ over R. Okay? So the potential at location 1 we would calculate by putting just our values in. So V would equal KQ over R. What's the value of K? 9 times 10 to the ninth. Okay, and then what value am I going to use for Q if it's relative to this negative 1 Coulomb charge? Yeah, I'm just going to use negative 1 Coulomb. Okay, and I'm going to divide it by the distance it's away from it, and what's that value going to be? Okay, so 1, so I'm going to leave the unit, I guess I'll put the units in there. So at location 1, the potential is what value? Good. It's equal to negative 9 times 10 to the ninth. What units? Volts. So I'm going to label that right here. So right here, it's negative 9 times 10 to the ninth volts. Okay? So the potential at location 2, I would calculate a very similar way. I'm going to use K, which is 9 times 10 to the negative ninth, or ninth, I should say. I'm still using the same charge, negative 1 coulombs, and I'm going to put in the distance. The new distance for location 2 will be what? 2 meters. And that value is actually equal to, that's actually pretty easy, right? What would that be? Okay, negative 4.5 times 10 to the ninth volts. Okay, so over here at location 2, I got negative 4.5 times 10 to the ninth volts. All right, so this next question says a positive test charge initially at location 2 will move in what direction? So if I put a positive test charge at location 2, it's going to move towards what location? Or it's going to move which way?
Towards the left.
Good. It's going to move left, okay, toward location 1, although it could keep going, right? Towards location 1. All right, because remember, a positive test charge goes from a high potential to a lower potential. So that's why it has to go left. Okay? What about a negative test charge? If we put a negative test charge initially at location 1, what direction is it going to move in?
Right.
Okay. Good. It's going to move right because a negative test charge moves from a lower potential to a higher potential. Okay, so it's going to move to the right toward location 2. Okay, now if we had to calculate how much work it will take to move an electron from location 1 to location 2, how would we do that? Any ideas how we would do that? If we had to move an electron from location 1 to location 2, what equation would I start off with?
Change in energy is charge times voltage.
Good. So the work in this case, which is going to be, they use U for the energy, is going to be QV. All right. Specifically, it's going to be Q delta V. All right, what is the charge of the electron?
6 times 10 to the negative 19.
Good, negative 1.6 times 10 to the, is it negative 19th? Negative 19th, and what are the units? Coulombs. And I'm going to multiply that by the change in the potential. So the final potential will be at location 2, so that value is what? Yeah, negative 4.5 times 10 to the 9th volts. And I'm going to subtract a negative, I'm put another parentheses there, negative 9 times 10 to the 9th volts. So I guess I gotta do a double parentheses there. All right, so I won't calculate that out, but that's how you, that's how it would be solved. Okay. So far, what do you guys think? Did I completely intimidate you guys with electric potentials? Remember I told you kind of, is it? Okay. Not that bad. All right, now, a really important topic is this. Electric potentials are not vectors. So does that make solving these types of problems easier or harder than electric forces and electric fields? Way easier, right? We like electric potentials. So for example, if I've got a negative 2 charge here and a negative 1 charge here, and I wanted to figure out what its potential is at location A, what would I have to do? Just add up the answers, okay? So if you'll notice, if you look at your equation sheet, you'll notice that there is a sigma sign in there, okay? And that just means just add them up. Yeah, the sum of. So in this case, I would just take the potential of KQ over R. It's supposed to be K. KQ over R. Remember, that's the equation for the electric potential of just one charge, plus KQ over R, and I would simply just add them up. Okay? So that would equal, can someone get their calculator out for us so that we can solve these? So the first K would be 9 times 10 to the 9th. And we'd multiply that times negative 2 coulombs. Okay, over 1 meter. Plus the other charge would be 9 times 10 to the 9th times negative 1 coulomb. And I'm going to divide that also by 1 meter. Can you guys give me a total answer for that? Would be negative what now?
Negative 2.7.
10 to the 10th volts. Okay? So, in calculating this out, Q for the electron in this problem, Q for the electron, we said it would be what?
Q would be...
What's Q? Yeah, negative 1.6 times 10 to the what? Negative 19 coulombs. And I got to multiply that by the change in the potential. So if I had an electron way, way out here, okay, if this is considered infinity, all right, and I moved it way over to this point here, my final position, the potential would be what value? Good. Negative 2.7 times 10 to the 10th volts. And I'm going to subtract, what would be the potential out here way at infinity?
0.
Okay, way at infinity, the potential would be 0. So I would get the amount of work that it would take to do that as what value? What are you guys getting when you plug that in?
Calculations, please.
Someone get that for me, please? It's a good thing I get to...
4.32
what do you get?
4.32 by 10 to the
4.32 times 10 to the what now? Negative 9th? And that's going to be in what units? Anybody? Good, that's going to be in joules. Okay. Another question that comes up a lot on the AP test are these ideas of gravitational, what I call gravitational well analogies. All right. So here's what I'm going to do. I'm going to look at this positive test charge. Okay. It's in between two really large point charges. So, I'll label that as a test charge. Okay. If we look at this from a completely gravitational point of view, this is what the analogy would be. This would be similar to a ball at the bottom of a valley, right? Because if I took that ball and I pushed it up here, which way would it, and I didn't push it hard enough, what would it do? It just roll back down, okay? It would do the same thing either way, right? If I try to push it up there and I didn't give it enough energy, it would just roll back down. Okay? Now, what would that analogy be if I've got a negative test charge in the middle, and two really large point charges on either end? What would the gravitational analogy for that be? Good. Exactly. So that would be like if it were on the top of a hill. Okay? Because all I got to do, because when it's at the top, it's balanced. It's going to stay there. But if we just barely push it, it's going to roll down the hill either this way or that way. All right? Okay. Is there